So we're going to talk a little bit about how we control lazy evaluation. So far we've talked about many of the positive aspects of lazy evaluation, for example, that it does in principle do less work than some other evaluation strategies may often do. And that leads us to, that opens up for new programming styles, for example, programming with streams of data or infinite data structures. And that as we've seen, interacts with I/O when it works well. But it doesn't always work well, and it doesn't always do the things we want to do. And so for advanced programming purposes, Haskell includes some features that allow us to control the amount of laziness. And this is closely related to when we perform parallel programming in Haskell, where we want to control how computation is performed. We're not going to get into parallel programming in this course. There is, in fact, a whole dedicated course for parallel functional programming. But it's worth mentioning both some of the downsides of lazy evaluation, the things that don't always work as we'd hoped, and the ways we can go about trying to fix those. So I'm going to start with a very simple function to illustrate this, and that is the sum function we have here. So this is a very basic, naive function for summing the elements of a list. What could possibly go wrong? Well, let's try it out on a big list. So I've called this sum 0, and I'm going to take the list from 1 to 10 million. So the sum of the elements from 1, all right, let's just start with 1 million, just as a warm-up. Sum of the elements from 1 to 1 million. There's a nice, pleasing round number. Okay, let's go a bit bigger, and let's take 10 million as our sum. That's going to take a fair bit longer, but we'll get there in the end. In fact, we won't get there in the end. We get a stack overflow. We've run out of space. And why is that? What has gone wrong here? Well, what has gone wrong is that if we start unfolding sum 0, if we write this in a comment, or maybe I've got a slide that will illustrate this. Just give me a second here. Yeah, there we go. So this is the example we just looked at. At the time I wrote the slide, 1 million was enough to get a stack overflow. Now I need 10 million, but same. Now, first thing, important thing to say is this is not a problem for lazy evaluation. This has nothing to do with lazy evaluation. This has to do with the way that we are writing our recursive definition. The way that we write our recursive definition forces us to compute this sum as the following expression. We're going to add 1 plus brackets the rest. And what's the rest? It's 2 plus brackets the rest. So what happens here is that we can't compute this first plus until we've computed everything else. So when we start to build this expression, as we're starting to compute, we need to put some of it on the stack. For example, the plus 1, we have to remember, we've got to do plus 1, but before we can do that, we have to compute the rest. So we put this 1 plus on the stack, and then we do the rest. Then we put the 2 plus on the stack, and so on. And we're building up this computation on the stack until we get to the very last element. Then we can start taking that additions off the stack and completing them. And then, not surprisingly, if we do this with too many things, we run out of stack. We don't have a big enough memory allocated in our interpreter or compiler to compute the answer. Now, this is not a problem of lazy evaluation. This is a general problem that we have when we compute things with this style of recursion. Now, the general recipe for getting a space-efficient recursive definition is to use tail recursion. So tail recursion refers to a recursive definition where the result of the recursive call is the result of the whole answer. So in this example, it's not tail recursive because the result of the recursive call is not the answer. We have to add n to it. We have to do something with that result in order to get the answer. Here's a tail recursive version. And we've seen this style of example a few times. It's the style where we use a helper function. I've called the helper function S. And that helper function has an extra parameter, and that's the accumulating parameter in the case of a tail recursive. So we're going to build the result in this parameter. We saw this kind of example when we looked at the reverse function in one of the very first lectures. So the way that it works is we're going to sum the elements of a list by using a recursive function with an extra parameter, and the extra parameter will store the sum so far. So it starts off as 0 because we haven't started summing things yet. And here's the definition. When we have the empty list and we've accumulated a sum, then that sum will be the answer. When we have a non-empty list consisting of a number and some other numbers, we recursively call our helper function, but we add the number onto the accumulator. We accumulate, we sum up the number, and then continue summing the rest of the list. So a tail recursive summation operation is the standard way to fix this stack overflow problem. It's worth noting that when we use tail recursion, it's something that will prevent us from lazily using a list result. So typically, unless we have to, for example with the reverse function, we wouldn't use tail recursive functions to construct, in Haskell, to construct list valued arguments or any kind of lazy data. So integers are not lazy data structures. You either have all of it or nothing. But lists are lazy data structures. You can have some of it. And the reason is because if we use tail recursion everywhere, we kind of block the good features of lazy evaluation. We stop the functions from producing any of their results until they're completely finished. Now, for the reverse function, which was our typical example of such a function, that was an inevitable feature of reverse. You can't produce any of the results of reverse until you've got to the very end of the list anyway. Okay, so this notion of tail recursion, and in particular combining elements of a list using tail recursion, is actually a standard computation pattern. It's a form of fold. We saw fold R. This is folding from the other end. We're sort of folding from the left. So we're accumulating elements from the left-hand end. And this is the standard pattern. It's called fold L. And so this sum1 function could be encoded, could be written as fold L with the addition operation and the base case 0. Now I can't illustrate this easily here, but in fact this will still have a problem. It may not be a stack problem, but let me just save and reload this file. If we try it with sum1, it may work actually, but that's just because we're moving stack onto the heap, but we'll see. This will be as big a surprise for you as for me. Yeah, so this one actually does work. And you see it also has this pleasing pattern, but with an extra 0 on the end. So this is better, but it's not better in space. And I'll explain why.